For this one, you should be able to explain the alloy structure and analyze the phase diagram. Number 2, all of you should be able to understand and analyze the ion carbon system. And number 3, you should be able to determine different phases of metal alloys using phase diagram. As for the lesson objectives, at the end of the semester, students should be able to analyze the physical properties of engineering materials and the concept of corrosion and metal alloys microstructure, phase diagram, and heat treatment process. Well, basically for today, we are going to look at on the phase diagram itself. Yeah, and for the content for today's topic is number 1, metal alloy. Number 2, phase diagram. And so this is the content outline, things that we are going to look at on the alloys, where it actually represent on the combination of combination between 2 or more materials into pure metals, which finally being called as an alloy. From there, we are going to look at its phase diagram, the microstructure of the materials from when it is solidified, and then substitutional solid solutions, interstitial solid solution, as well as intermetallics. After that, still in chapter 4, in however part 2, we are going to look at on ferrous materials as well as non-ferrous. After that, we're going to look at on the heat treatment, which includes quenching, annealing, tempering, normalizing, solid solution treatment, precipitation hardening, aging, and so on and so forth. We are not going to cover everything, but most of the important process will be covered in this subject. And I think more detail on those processes of the heat treatment you're going to learn in manufacturing process. So the definition for alloy is that it is a materials which consists of 2 or more materials to perform that specific function of it. However, its crystal structure will not be changed even though it combines different types of materials in it. The substitutional solid solution size similar to the solvent. Yeah, it has to be similar. Otherwise, it is very difficult to produce new type of alloy. And then interstitial solid solution, size much smaller than solvent atom. We'll see the example later on. Same goes to the phase system itself. We may see two or more different solid phases exist on that microstructure. For example, sand and water, yeah, or ice in water. And if you look at these two diagram over here or illustration over here, figure A is showing a schematic illustration of grain boundaries there, and a particle dispersed throughout the structure of two phase system, such as a lead copper alloy. The grain represent lead in solid solution in copper, and the particles are lead in a second phase. Meanwhile, for figure B, it shows a schematic illustration of a two-phase system consisting of two sets of grains, the dark one and the lighter one. The dark and light grains have separate composition and properties. We'll see more details about this in phase diagram afterwards. So for phase diagram, the most phase diagrams actually showing a mixture of phases present in thermodynamic equilibrium. It tells you what are the phases present in a given temperature as well as the composition. And it is very important for you because it can be used to predict the behavior of the materials. Okay, this is an example of phase diagram for water, H2O. You can see there's a point A and point B there, and phases are separated by the boundaries of this boundary. This line is actually boundary, the blue line and also red line over there. And for H2O, there's a triple point for point A exists over there. All right, so phases available for H2O is that water, liquid, solid, and vapor. This is liquid phase, solid phase, and vapor phase. Well, it's all depending on the temperature of the phase diagram. In the phase diagram, we may also find a term which is called a solubility limit. If we refer to this phase diagram, solubility limit is this line. Okay, it's a line between a liquid and a liquid plus solid. So for this case, this is for a sugar and water phase diagram. And let's do example of the question asks you to determine the solubility limit for sugar in water at temperature of 20 degrees C. So if you look at this diagram over here, 20 degrees C for temperature, at this point, at this line, you may need to pull the line or make a line from temperature 20 until it reach this a line, solubility limit line there. And from there, you need to determine the solubility limit value or percentage from x-axis, which in this case equals to 65 weight% of sugar. So we can say that more beyond lower temperature for this point for 65 weight percentage of sugar. If the temperature lower than 20 degrees C, we can say that the phases exist is that mostly syrup, because this is a liquid phase, so we don't see sugar in the syrup. However, if the temperature is more than 20 degrees C, you can see more than 20 degrees C. For example, if we take 40 degrees C over here, so taking there at that point, so we can see there's two phases exist in it, which is syrup itself plus sugar. And same goes to if we increase the temperature until 60 degrees C, making a line from this point until it reach this line, the boundary over here, then it reach this phases, which is liquid plus solid sugar. And the rest of the terminology, I think you can read it on your own, starting from solution, mixture, solvent, and so on and so forth. Same goes to this one. So in terms of microstructure, if the composition reaching a two or more phases, you can see what are the differences between components and phases. Or components, it represents the material itself or the alloy, which combining different materials, two or more materials in it. For this case, aluminum and copper alloy. And in these components, we may find different phases in it, like alpha phases and beta phases. So we can say that from this phase diagram, if we change the temperature, we change this temperature, y-axis, the phases will move from path A until path B. And same goes to x-axis over here. If we change the composition of sugar percentage, we are actually changing the phase from B to D over there. Okay, criteria for solubility limit, as I mentioned to you just now, if it is also known as substitutional solid solution. So for that case, the crystal structure, electronegativity, and atomic radius has to be the same. Otherwise, it is very difficult to have a solubility. Sorry. Very difficult to have a solid solution for this case. Example is nickel copper solution, whereby nickel copper solution have no unlimited solid solution, which means you can add any percentage of nickel in copper or copper in nickel, and you may not found a situation which happens in sugar and syrup just now, because sugar and syrup has the solubility limit, whereby at some point you may also see sugar in a syrup because that sugar can no longer dissolve in syrup. And in phase diagram, these are the terms that you need to know, which is liquidus, solidus, and solvus. Solidus represent lined line representing the temperatures at which various compositions begin to freeze upon cooling. Meanwhile, for solidus, it is actually a line representing the temperatures at which various compositions finish freezing upon cooling. And number three is for solvus. It's the line representing the limit of solubility, or a line separating solid phases. We will see these lines in the next slide. Okay, taking example for copper nickel system. This is copper nickel phase diagram. So if you refer this diagram over here, how many phases available or exist in this system? Yes. Well, the answer is already over here. Okay. However, there are two phases occur in this phase diagram, which is liquid, the upper part, and solid, which is the lower part. However, there are three different phase fields, which is liquid, solid, and in between there is there is a liquid plus a solid in between there. Okay. Other than that, we may also you may also come across with isomorphous, and isomorphous actually represent one in which the solid has the same structure for all compositions. In isomorphous systems, the two components have unlimited solubility, which means that they are like water and alcohol when they mix. So, like I mentioned to you just now, solubility limit for copper and nickel system, no limit for you to add a copper into nickel or nickel into system, because the phase diagram itself showing you there's no solubility limit for these types of phase diagram. Okay, so I did mention for this system. And binary referring to a phase diagram which have two components. For this case, copper and nickel. Okay, in phase diagram, we need to determine the percentage weight percentage of the solid phase and liquid phase which exists in between this line. This side. So how can we determine this weight percentage is by using a lever rule. Lever rule is like a T-tutor. You can imagine a T-tutor over there. And okay. So but you need to know the value of C naught, and from there you can draw a line from liquidus line until reaching a solidus line. So this is the level rule. From using this line, you may calculate the weight percentage of liquid exists in this phase. Same goes to solid phases exist in this phase. And the formula is shows as follow. For example, for liquid phase, S over divide by R plus S. Or, I mean, for this one, if you're referring to x-axis, C alpha, composition for solid there, yeah? C alpha minus C naught divide by C alpha minus C liquid. So you should be able to get the value of weight percentage for liquid phase exists in this area. Same goes to solid phase. R, this one is R divided by R plus S. Or if we are referring to the x-axis, C naught minus C liquid divided by C alpha minus C liquid. Okay, so this is okay. Again, showing you a copper-nickel phase diagram. So this is how you calculate the solid fraction, and this one is how you calculate the liquid fraction. Formula is the same. I just rewrite it again, showing a full a full phase diagram for copper and nickel. So you might see the overall phase diagram. Okay, so for phase diagram, rule number one is that if we know temperature and C naught, then we should know the phases present. For example, for this one, the phases available is okay. Phases available at this point. If we know the temperature like 1100 with C naught equals to 60% of nickel, so we know that it is at this point, which is point A. So this one falls under solid phases, which is alpha phase. And for case B, we know that the temperature is 1250 degrees C with C naught equals to 35% of nickel, which falls in this section, this area, this phase. So two phases exist at this area, which is liquid plus solid, or L plus alpha over here. Move on to rule number two. Rule number two saying that if we know temperature and C naught, then we can determine the composition of each phase. For example, at TA represent the temperature for 1320 degrees C. And then we know that C naught is 35 weight percentage. So moving up over there, then we know the composition for liquid equals to C naught, which is equals to 35 weight% of nickel. Now let's look at point D with the temperature of 1129. C naught is the same, still the same, which is equals to 35 weight percentage of nickel. So this point reaching point D. And from here we know the C alpha or composition for solid, fraction for solid equals to C naught, which is 35 weight% of nickel. And however, at point B, with the temperature of 1250, C naught still the same, which is 35 weight percentage, and it falls at the area with both alpha and liquid, solid and liquid exist over there. So from them, how can we know the percentage of nickel? Is that by drawing a line reaching a solidus line and liquidus line. So from them, we know the value of Cl equals to 32. Meanwhile, for C alpha equals to 43 weight percentage of nickel. So that's how you determine the composition of each phase by following a rule number 2 for phase diagram. Now let's move on to rule number 3. It says that if we know temperature and C naught, then we can determine the right fraction of each phase. So considering C naught still the same, which is equal to 35 weight percent of nickel. 48 just now, the value of weight percentage, weight fraction for liquid is equal to 1 or 100% in that part. For this point A, 100% liquid or WL equals to 1. Remember the formula for liquid just now, S divide R plus S. Okay, how about point D? So point D just now, 100% solid, so no liquid at all. Formula is the same like I mentioned to you just now. All right. However, for point B, you are going to find the weight fraction for liquid and solid is different. So using a level rule, you need to draw a line touching liquidus and solidus line. After that, draw a line for C naught, and you may find R and S value there. From there, you can calculate the value for weight percentage of solid, which equals to S divided by R plus S, or in this case, 43 minus 35 divided by 43 minus 32. So you should be able to get the value of 0.73. Same goes to solid. You should be able to get the value of solid weight fraction, which is equal to 0.27, or in this case it refers to 27%, and this one 73%. Okay, other than that, this one we calculate the weight fraction for each phase, and from phase diagram we may also determine its structure. So let's take the same example, which is copper nickel system with C naught equals to 35 weight percent. At point B, upon cooling, this is liquid, meaning it is already heated until it reach liquid phases, and then upon cooling, once it touch this liquidus line, then it starts to cold, which in its microstructure it starts to have a solid which is called proeutectic in this structure, a dotted line there. After that, moving to point C, the solid faces there starts to grow bigger, and then reaching point D, it grew much more bigger with a blue color over there, and one is reached 100% solid, then all the area being dominated by solid with a grain structure over here. So basically, if you want to control the microstructure, then we need to know on how to control the temperature as well as the percentage of the composition. Well, as you learned in previous topic, previous lecture, the microstructure may affect the final properties of the materials, and the structure of the materials, we can control it by using this phase diagram, and of course you need to know the process involved to change the microstructures as well. Well, it's actually referring to the process and you may learn it in detail for in manufacturing process for that part. Okay, what happened for this part? Okay, once it is start to cool, okay, slow cooling. For slow cooling, you may have these types of a structure, equilibrium structure. But for fast cooling, you may have this what we call the pro-eutectic, whereby the solidification starting from the core and moving outwards, which means that the outer part over here is last to solidify. And okay, I did mention to you these things just now by taking example of copper and nickel. The properties like its tensile strength, the elongation of it may change due to the structure. Okay, for this case, for example, if 0% of of nickel over here, I mean this one is pure copper and this one for pure nickel. Pure copper may have tensile strength with 200 megapascal. Meanwhile, for pure nickel may have like 320 tensile strength. However, combination of both materials may have higher tensile strength. So what happens to the microstructure? Okay, and same goes to elongation. Okay, let's do this example together. A copper nickel alloys contains 74% of copper. So 0 to 100% for nickel over here. And the other way around is meaning this one 0 copper and this 100% copper. 47 weight percentage. 47, where is 47? Oh, sorry, this one we use 53% of nickel. So 53, this line. So this is the W naught or C naught for nickel, 53%. And question asks you to determine the weight percentage of copper in liquid and solid phase in temperature. Number 2, weight percentage of this alloy is liquid and what percentage of solid. So let's do this example together. The intersection of 1300 degrees C tie line with the liquidus gives 55 weight percentage of copper in liquid phase, and intersection giving you lines 42 weight percentage copper in solid phase. This one. Okay, we know that C naught, which is equals to okay, so you ask for copper, yeah. 47 or 53, so this point, and you need to draw a line touching a liquidus and solidus line. From there you should be able to get the percentage of copper over here for a liquid and this one for solid, which is 55 and 42. This one 55 and this one 42, 42, 45, 42, and this one should be 55. Okay, then the fraction using the same formula for liquid phase, S over R plus S. So you should be able to get 0.38. Same goes to solid, which is R over R plus S. You should be able to get 0.62 or 62 weight percentage. Now, phase diagram consists of two components, is known as binary system. And if the diagram showing you a binary eutectic system, it means that these two components has a special composition with a minimum melting temperature. Eutectic point is this point. So from diagram, phase diagram just now, you don't see this point. I mean the eutectic point, like this one. For this diagram, for copper nickel phase diagram, there's no eutectic point over there. However, for this one, there's a eutectic point over here. So what are the phases available for these types of phase diagram? And let's take example for copper silver system. For this one, there's a three phases exist, which is liquid, alpha, yeah, B or alpha or beta. This one alpha and this one beta, A or B. And other than that, you may also found a phases alpha plus liquid, and this one alpha beta plus liquid. And at this point, it is all it is a combination of alpha plus beta or A plus B over here. And okay, at the point of eutectic reaction, at this point, from liquid, okay, let's refer to this line. From liquid, it starts to solidify, touching to this point. There you should be able to get two phases occur, which is alpha and beta, with the percentage of alpha which is equal to 8 with percentage of silver, and B which is 91.2% with percentage of silver. Same goes to the heating situation. Once you heat this alloy from here, solid, yeah, from solid, you start to heat and reaching a eutectic point, and it will change straight away into liquid. As compared to this point, for example, if we take 40% of silver, you start to heat the alloy, and reaching this line, it will change into liquid plus solid alpha first before it change into 100% liquid. So that is the special thing about eutectic point. Okay. What will happen to the microstructure in this phase diagram? So let's look at the example. This one by not referring to the eutectic point, but we are referred to C equals to composition equals to 40% of tin. So from liquid over here, yes, liquid, you may have only one phase, which is liquid over there. And after reaching a solidus line over here, it started to have liquid and solid phase in it, whereby the element of alpha start to grow, okay, which is called as pro-eutectic there. Alpha element there. And then moving to this line, the alpha solid starting to grow a bit bigger compared to point K over there, and passing that line, passing the cooling line there, everything changed into solid, 100% solid. However, the structure is slightly different, because you may have a primary alpha there, but at the same time, we may also find a lamellar structure. This is a lamellar structure which consists of beta tin and alpha tin, which is known as eutectic structure. Okay, this one is the same as this. However, what happened to a microstructure which solidify at the point of eutectic, using eutectic point? So this is the eutectic point. This is what will happen to your microstructure when using a eutectic temperature. Okay. So this is also the same. Okay, now let's look at the example. Let's do this together. Yeah. This is a plumbum and tin system phase diagram. For 40 weight percentage of tin, 40 weight percentage tin and 60% of plumbum, so 60% plumbum then. At 150 degrees C, determine the phases present. For T naught, we know that 40% and temperature 150 degrees C. So at this point, so we know at this point we should have everything is solid. However, what solid is that? Solid consists of beta and alpha. Okay, and how about its percentage? Percentage of alpha. Okay, from this point you draw a line there until you reach this line. So point here represents C alpha equals to 11%, and meanwhile for beta this point is 99% of tin. And after that, that is the phases present. And what are the percentage of solid and liquid exists in that case? I think this is the other example there. So this question is only up to this point, and this one for the other phases. Okay, never mind. We choose this example number 2. Okay, so again the same phase diagram. It asks you to the I hold on, yeah. Okay, this one is correct. So sorry. So for this one, temperature given is 220 degrees C with C naught value is equals to 40 percentage. So it falls until it falls in this phase, which consists of liquid and alpha solid. So from there, use the level rule, and you may get the value of C alpha equals to 70%. Meanwhile, for liquid, which is 46%. And what are the weight percentage or weight fraction for liquid and alpha in it? So using a level rule just now, weight fraction for alpha equals to S over R plus S. So you should be able to get 0.21. Meanwhile, for liquid, R divided by R plus S, and you should be able to get 0.79 or 79 percentage of liquid there. Now, this is the microstructure for this one. Okay, solidification starting from liquid phase. After that, touching that line, solidus line, it starts to have a alpha primary, so for primary solidification, and then after that line, 100% alpha. So this is the microstructure for alpha with the green boundary there. And well, this one, if you notice from the phase diagram, this will happen if the percentage of the percentage of tin less than 2%. What will happen if the C naught or tin percentage is in between 2 and 18.3, which is before this point there. So this is the microstructure that may exist. Liquid, after solidification, starting from liquid, reaching to this phase, you should be able to get two different phases over here with primary alpha and liquid. After that, once reaching a phase for solid alpha, then you have 100% alpha there. And After this line, after this line, you are reaching a phase with alpha plus beta. So after solidification, you should be able to see there's a precipitation of alpha of beta in alpha microstructure, which is appears in a dot. And what will happen to this phase diagram when it is solidified at eutectic point? So starting from liquid, this is liquid reaching a eutectic point and straight away change into alpha plus beta solid phases, which in lamellar structure like this. Okay, lamellar structure. So this one consists of alpha and beta with how many percentage? Well, you need to refer to phase diagram. You need to draw line from here until it reach line B. So alpha, you should be able to get 18.8% of tin. And this one for beta, you should get 97.8% for tin. And in real life, this is how you may see the microstructure for plumbum and tin phase, plumbum and tin alloy. Okay, this one a close up for lamellar structure. The size is the same, plumbum and tin. And you may also calculate the weight fraction for solid and liquid for both alpha and beta, as well as a liquid phases which may exist. For example, this one above TE, slightly above TE, before reaching point eutectic there, you should get this line. Okay, should get this line, and from there you can calculate the value of the alpha weight percentage of solid alpha and liquid phase which exists in that microstructure for this one, for these types of microstructure. And slightly below eutectic point, which is alpha equals to 18.3% and beta equals to 97.8 percentage of tin there, you may find these types of microstructure. Okay, remember again, at this phase, which is alpha plus beta, you may have a lamellar structure consists of alpha, eutectic alpha and eutectic beta, plus with the primary alpha in it because of this solidification line. Okay, so from there, using the same formula, you can calculate the value of alpha and beta weight fraction. And if we refer to the original microstructure, these are the microstructure that you might found. This one for before eutectic point. Okay, you may see lamella plus alpha alpha phases in it, and this one lamella plus beta in it, but this one is 100% lamella and beta only passing through eutectic point. And below eutectic point, for this case, below eutectic point is known as hypoeutectic, and above eutectic point is known as hypereutectic. And other than phases in phase diagram, we may also find which is known as intermetallic compound. These intermetallic compounds, or IMC in short, we may not find it exist in phases. However, it exists in line. For example, this one, magnesium plumbum. This line represents a intermetallic compound. While intermetallic compound exists due to diffusion, solid diffusion or liquid diffusion between two or more materials, or alloy, and it will form intermetallic compound. Okay. So sorry. So just now you have learned on the eutectic point, which is a point where liquid transform to two solid phases. For example, tin plumbum just now. Um, for tin plumbum at temperature of 183 degrees C with C note 61.9 with percent of tin from liquid. It cools a solidification. After solidification, it starts to form two solid phases, which is alpha and beta. However, there is other point in phase diagram which is known as eutectoid. Eutectoid refers to one solid phase transformed to other solid phases. For example, this one, cementite, gamma, sorry. Gamma, after solidification, it starts to form two other solid phases. This is solid, solid 2, if solidify, forming solid number 1 and solid number 3. So if we are referring to iron carbon phase diagram, which you have seen in previous lecture, um, passing through eutectic point, you'll see alpha and cementite. Well, cementite is actually intermetallic compound for that phase diagram. And other than that, we may also find a peritectic. Peritectic represent a liquid and one solid phase transform, liquid and solid phase transform to a second solid phase. Okay, first solid plus liquid transform into second solid phase. Or for iron carbon system, at this temperature with 0.16 weight percentage of carbon, you may see delta plus liquid solidify forming a gamma solid phase. We'll see this example later on. Okay, so this is the copper zinc phase diagram, and this one referring to eutectoid transformation. You see, this is a delta passing through, after solidification, passing through eutectoid line, eutectic point, and forming gamma plus epsilon there. Meanwhile, for peritectic, okay, solid, after solidification, starting from this line, solid plus liquid passing through peritectic point and forming a solid delta. Okay. So you see, not all alloy may have this point, may have this line, peritectic or eutectic point. Well, it depends on types of materials. So you don't have to worry, not all materials may have these types of transformation. This is the another example for a peritectic system. And same goes to this one. Well, actually, this phase diagram showing you what will happen to the microstructure after passing through a different phases for binary peritectic system. Okay. And other than that, you may also calculate the weight fraction of each phases, liquid and solid, or solid and solid, using the same formula, which is using a lever rule. And other than that, there's also called as binary monotactic system. Monotactic reaction represent liquid phase transform into solid phase and another a liquid. And for example, copper lead system at 955, which is 955 degrees. This is 1955 degree. And 36 plumbum over here. So this is monotactic reaction. Okay, one liquid transform into solid phase and another liquid. All right. And in summary, this is the reaction for binary phase diagram: eutectic, eutectoid, peritectic, peritectoid, and monotactic. And this is the equation. I think this is the summary for all the transformation of phases in phase diagram. So now I'm gonna refer it back to our iron carbon phase diagram. And if you still remember, our phase diagram have a different phases exist, like a ferrite, austenite, alpha ferrite, delta ferrite, and also cementite, which is the intermetallic compound. Okay, so this is again the phase diagram for iron carbon, iron carbon. All right. Um, these are the explanation on phases exist in iron carbon phase diagram. And I think this one you can read it on your own because it's only an explanation on where does it exist, at what temperature, what are the crystal structure, as well as its properties. Okay. But however, please refer to this diagram. All right. So that you may understand it better, where are the location for each phases, like this one. This is the ferrite. Okay, location of ferrite or alpha. Okay, this is liquid phase, and this is the delta phase over there. Okay, this is austenite or gamma, and this one is gamma plus liquid. This is gamma plus cementite, and this is alpha plus cementite, and cementite is this line. Remember, cementite is intermetallic compound and it won't exist as a phase in phase diagram. However, it will only exist in a line base. Okay, alpha ferrite, austenite or gamma, delta ferrite, cementite. And if you notice in phase diagram just now, there's a peritectic reaction occur as well as eutectic reaction. For peritectic, for example, yeah, after solidification, liquid plus delta, it will form gamma. Okay, let's look at this one. So peritectic, alpha plus gamma. Okay, so this is peritectic. Liquid plus delta producing a gamma. All right. For eutectic reaction, for eutectic, this is the eutectic point from liquid passing to eutectic point, producing delta plus cementite. Okay. And there's also eutectoid reaction exists in iron carbon phase diagram. Oops, sorry. This is eutectoid. Okay, so from solid gamma, solid austenite, passing to eutectoid, producing alpha plus cementite. Okay, so material or alloy which consists of less than 0.76% percent of carbon is known as hypoeutectoid steel, and those are having more than 0.76 weight percentage of carbon is known as hypereutectoid. Again, refer to this phase diagram. This is 0.76 weight percentage of carbon, which is eutectoid point. So Lower than this is known as hypoeutectoid, and beyond this point is known as hypereutectoid. So you need to know the terminology for this reaction. Okay, what will happen to the microstructure for eutectic? For the eutectic, you may have a gamma plus cementite over here. As for eutectoid, from a solid, so solid gamma or solid austenite passing to eutectoid, you have a lamellar structure as well. The lamellar part is the cementite, which is very hard and brittle. However, austenite is the metric itself with very soft properties. And this is the microstructure for eutectic. Okay, eutectic from sorry, eutectic, not eutectic. This is eutectoid. Okay, again, the lamellar part is the cementite, and the metric itself is gamma or austenite. And okay, for iron carbon alloy above and below eutectic temperature, the mechanical properties of pearlite are intermediate between those ferrite and cementite. Okay, and less than 0.76% carbon consists of pearlite phase and ferrite phase. The ferrite phase is called proeutectoid ferrite, forms at temperature higher than eutectoid temperature, which is 7 to 7 degrees C in the alpha plus gamma region. I think this one you may also want to refer the phase diagram for a better understanding. And number 3, more than 0.76 carbon austenite transform into pearlite and cementite. The cementite in the pearlite is called eutectoid cementite, and the cementite phase is called proeutectoid cementite. This is the hypoeutectoid steel. This is what is being explained to you just now. And in real life, this is the microstructure that you may find for hypoeutectoid, which is the value of carbon equals to 0.358%. Okay, again, after solidification, this is solid austenite passing through this line. You have a austenite and also alpha at the grain boundary. After that, it starts to grow bigger there, and passing through the eutectoid point, you'll have a pearlite, which consists of alpha plus cementite. It's called as pearlite. Okay, and alpha. All right. Okay. Again, and in using this phase diagram, you can calculate what are the percentage of alpha, gamma, and cementite exist using level rule just now with value with the formula like S over R plus S or R divided by R plus S. Okay, if you notice over here, yeah, we are referring to the ratio, which means that it is need to equals 100% or 1. And if you have calculate the value of alpha over here with the formula of S equals to R plus S, then the value of gamma is actually 1 minus this one. 1 minus a weight fraction for alpha. So same goes to this one. So basically, either formula is applicable. So it's up to you which formula you want to use. But in the end, the total has to be 100% or equals to 1. Hypoeutectoid steel. Okay. So these are the microstructure that you may found. Okay. And this one is for hypereutectoid steel. Okay, you may look at to the structure, the microstructure over here, what will happen after solidification. And this is the real microstructure that you may found for plain carbon steel. So basically everything from phase diagram over here is through slow cooling. Later on, which is in part 2, we are going to look at on fast cooling. While the process of the cooling or solidification process also may affect the final structure of the materials, which finally will affect its own properties. All right. Again, the same thing. You may calculate the weight percentage or weight fraction for each phases. Okay, now let's do this example together. I think I have few example for this slide for this topic today. Okay. For steel carbon phase diagram, using a point eutectic point, find the composition of ferrite and cementite. After that, we need to find the amount of cementite in grams that form in 100 gram of steel. And last but not least, the amount of perlite and pro-eutectoid ferrite in 100 gram of steel. So the first step is the same, using a lever rule, which is RS line just now at eutectoid point. This is eutectoid point. Temperature is given, right? The percentage 0.02 for alpha, okay, and for cementite 6.7 percentage of copper, carbon. Okay, so that one is for question B. Next question A. So question B, using a lever rule formula, so that you may found the weight fraction for cementite equals to 5.7%. Meanwhile for it asks you to find the fraction for in 100 gram of steel. So times with 100 gram of steel, you should be able to get 5.7 gram of cementite in 100 gram of steel. For C naught equals to 0.4 weight percentage, C alpha 0.022, and C perlite or gamma equals to 0.76. This point. And using a lever rule, you should be able to calculate for gamma or perlite there, which equals to 0.512. And the amount of perlite in 100 gram, you just times with 100, you should be able to get 51.2 gram of perlite. Move on to example number 2. Considering 1 kilogram of austenite containing 1.15 weight percent of carbon cooled to below 7 to 7 degrees C. And what are the pro-eutectoid phases exist? Number 2, determine the weight of each of total ferrite and cementite phase. Number 3, determine the weight of each of perlite and pro-eutectoid phase. And number 3, sketch and label the microstructure that may occur in that alloy. So let's do this together. The pro-eutectoid phase will be cementite. Okay, since 1.15, which is 1.15, okay, somewhere here, is greater than eutectoid composition, which is eutectoid composition 0.76%. So cementite will occur over here. Okay, now using lever rule, you may calculate S over R, for solid cementite. R equals R divided by R plus S, and you should be able to get 0.17. In 1 kilogram, then just times with 1, you should get 0.17 kilogram of cementite in it. So can you imagine the properties of the materials once you have cementite, which is brittle, hard and brittle in nature? But then the amount is very low in it, so you can say that the overall alloy itself, my steel itself may have slightly may I mean still in ductile properties if we are referring to the hardness of it. Okay, question number 2. Again, use the lever rule and you may get the value of alpha equals to 0.83. Okay, this is the alpha. All right, and in 1 kilogram, just times with 1, and you should get 0.83 kilogram of alpha in steel. C, same, use the lever rule with the tie line 0.76 to 6.7. Okay, hold on, yeah. From here until this point, that is the tie line. And apply the same formula, you should be able to get the amount of perlite equals to 0.93 kilogram. Same goes to cementite. You should be able to get 0.07 kilogram of cementite. And this is the microstructure for this case now. All right, you may see the alpha ferrite there, and then eutectoid cementite, that one, and pro eutectoid cementite. Okay, so that is the overall part on the phase diagram, especially for iron carbon phase diagram. And you see, this phase diagram may change due to additional element in it, or which is known as an alloying element, alloying with other elements in the original alloys. What will change? Well, for example, eutectoid point. Eutectoid point may also change, or eutectic point may also change depending on types of alloying element that being added into that material. Okay, and you may see the graph over there with the changes of temperature as well as composition for each types of alloying elements. And this is what will happen to the microstructure, to the crystal structure. All right, even though it is BCC, FCC, or CPH. Okay, of course, when we add other alloying element, it can stay like here, like that, or like this. Okay, well, you may see if you look at in using a electron microscope, you may see a foreign particle axis in that crystal structure. So that is referring to the alloying element itself. Other than that, once we alter the composition of the materials, we may find it may produce other types of materials or alloy, which known as cast iron. Cast iron refers to ferrous alloy composed of iron and carbon, which is ranging from 2.11% to 4.5%, and a little bit silicon, which is up to 3.5%. So in summary, phase diagram are useful tools to determine the number and types of phases present, the composition of each phase, and the weight fraction for each phase at the given temperature and composition of that system. Number 2, the microstructure of an alloy depends on the composition and whether or not cooling rate allows for maintenance of equilibrium. And number 3, important phase diagram. Phase transformations include eutectic, eutectoid, and peritectic. With that, I thank you very much for your kind attention and time. I hope you do understand for this lecture. However, if you still do not understand, then you may contact me is either through group WhatsApp or Google Classroom, and I'll come back to you as soon as possible. And please be noted that this is very important topic. Please do a revision, and you may do more exercise using a reference book that have been proposed to you before, so you might understand it better. And if you notice, we actually already finished with chapter 3, and therefore we may have an quizzes or assignments later on. But for chapter 4, we still have part 2, which is in the next lecture. So with that, thank you very much. And see you again in the next lecture. Okay, bye.